All right. So before you commence with these sets of slides, ensure that you study or you go through the components in the video that is labeled Vision Processing Summary. Um, in this one, we just want to have a look at the processes that go on after the ganglions now have been after the impulse has been initiated in the ganglion cells. So for you to know what is happening between phototransduction to ganglion cell initiation of an action potential, you really need to get through that video. But as a summary, what we are saying is we have a change of potential from negative 40 to negative 70 when there is light. All right, this sort of hyperpolarization that occurs. And the phototransduction itself that occurs is such that you have the photons isomerizing the retinal to its all trans form, and this releases and activates the opsin. That is the type of configuration or change that goes on. And secondly, you see that this freed opsin acts enzymatically to catalyze activation of the G protein. To be specific, the alpha part of this G protein, the transducin in the rod, goes on to activate PDE. And once PDE is activated, um, we have uh, it's detached CGMP, all right, from the sodium channels by hydrolyzing it to GMP. So now that the sodium channels have no CGMP, they will close. All right. Specifically, uh, what we're saying here is once their ligand is detached, the sodium channels close, preventing sodium entry and causing hyperpolarization, which is what we had earlier referred to. Just as a reminder, PDE is also the same. That it's the same uh, substance that is inhibited in order for Viagra to work. You will learn about this uh, if you haven't already in reproduction physiology. So again, in the dark, CGMP, the gated channels, they open, allowing cation influx and um, photoreceptor depolarization. And then because of that, we have the voltage gated calcium channels open in the synaptic end, which is the one that is synapsing with the bipolars. The neurotransmitter is released continuously, and so it causes this hyperpolarization. IPSP stands for inhibitory postsynaptic potentials, all right? So since they're inhibitory, we find that there is hyperpolarization. The hyperpolarization closes the voltage gated calcium channels at the synaptic end of the bipolar cells, and this blocks the release of the neurotransmitter for the bipolar cells, which is, guess what, glutamate again. But glutamate in this case has an excitatory effect on the ganglion cells, but because it's not being released, there are no excitatory postsynaptic potentials that are occurring in the ganglion cells, and thus no action potentials occur along the optic nerve. So this is what's happening in the dark. In the light, however, we find that the CGMP gated channels close, and so the cation influx stops. So you have a hyperpolarization that goes on in the photoreceptor. In this case, we have a rod. The voltage gated calcium channels that's close in the synaptic terminals, and there's no or reduced. I like saying reduced instead of no. No is very absolute. So there's a reduction in the neurotransmitter released onto the bipolar cells, and um, there's a lack of IPSPs in the bipolar cells, resulting in depolarized state. So in short, 4 is saying there's no inhibition. Because there's no inhibition, there's excitation. And depolarization opens the voltage gated calcium channels, and the neurotransmitter is then released. So this causes an EPSP to occur in the ganglion cells, and an action potential is propagated along the optic nerve. So again, at 6, we have excitatory postsynaptic potentials that are occurring because of the release of glutamate from the bipolar cells. And as I said earlier, glutamate in this case has this excitatory effect, unlike the type of effect that it was having in the bipolar cells. And if you go back to the video, it explains more on this. At this point, I'd like you to refer to Dr. Katek's lecture on coding, where he talks about bipolar cells that have ionotropic receptors. These ones respond to glutamate by being excited. And so you see that because of this, you have two types of bipolar cells. And he explains more about on center, off surround, or off center, on surround types of coding. So this is the physiology on which it is based on. So please go back and redo that component. All right. Moving on, we're now going to see, now that there is an action potential that has been initiated in the optic nerve, where are we going? So we're now going to talk about neuropathways. So the summary of it is this. We have light. Okay, there's absorption by photopigments in the rods of the cones. Then there's the chemical reaction, which leads to a decreased transmitter release. And because there's a decrease in the neurotransmitter, we have the bipolar cells responding. Okay, and they will initiate action potentials in the ganglion cells. And now we have an action potential in the optic nerve. What then? So the visual pathway is such that it starts from the left eye and the right eye, okay, and it follows a very strict pathway from the left side of the eye and the right side of the eye, a very strict pathway. In that, if we follow the left eye, we're going to find the left side, uh, the axons coming from the left side going on to form this optic nerve. But as they reach what is called the optic chiasm, we find that they use the left side, they do not cross. But those ones coming from the right side, we find that they cross to the other side and keep on with a pathway. Whilst the right side of the eye, you have the left side of it crossing and the right side of it not crossing. So we're going to go through these details. But yes, this particular slide is just there for you to show, for it to show that the pathway includes these axons that are very specific in the way they move, and the optic nerve moves to the optic chiasm, where some of them decassette, and after that we have 90% of them synapsing at the lateral geniculate bodies that are part of the thalamo area. Okay, and then 10% of them go to the midbrain. We shall look at this, the 10% that go to the midbrain, when we look at the physiology of sleep. But most of them synapse in the LGBs, and then from the LGBs, we have them go to the occipital lobe. So this is a summary of how they move, and now we're going to go into details. And in going into the details, we're going to start from the top all the way to the details of the bottom. So as I go through these, I'll introduce new terms, I will introduce new mechanisms. So just make sure that you follow, and when where you don't understand, you can just rewind. And if you still don't understand, please make sure you ask questions on Slack, or ask questions, DM me on Slack. You can also ask questions on Google Class, but please ask if you do not understand. So let's now go into the details. So first of all, we're going to start with the field of vision. Okay, the field of vision is simply what you're looking at when your eyes are open and light is coming in. Where is it coming in from? Okay, so the field of vision is the visual area seen by an eye, okay, at any given instant. So at any given instant, even if you're looking or focusing at something that's right in front of you, there's certain components around your eye that are still in the uh, field of the vision. All right, so we're talking about what is the eye accommodating, or what rays are coming through into the eye. All right, so if we look at our right side, let's typically look at the right eye. You have two fields of vision. You have one that is coming from the temporal side. Now, the temporal side is the side of the ear, okay? And when I say nasal, it's the side of the nose. Okay, and I'm going to talk of nasal and temporal because I'm talking about one half. So if I talk about the right side, or I'm talking about the right eye, I'll talk about its temporal and its nasal side. Now, if you look at your right eye, I want you to take your left hand and put it on your nose, vertically up. Okay. Now, if you look at your right eye, you will see that the temporal side of the right eye, okay, is on the right side. Okay. And the temporal side of the left eye is on the left side. Okay. All right. Then let's go to the nasal. The nasal part of the right eye is on the left side. Okay. Whilst the nasal side of the left eye is on the right side. I need you to pause, rewind this part, and practice. Okay. So be very careful when in a question the field of vision is the one that is being uh, described. So if you look at the right eye, you see that the blue side, okay, is the temporal side. All right. So the blue side is the temporal side. So if you go to the other blue side, it's also the temporal side of the left eye. When you go to the right side, the temporal side is also shaded blue. And the nasal sides, or the nasal fields, are both of them, they are uh, just white. What if I change the way I'm describing these areas? Let's practice. Okay, so your answers should be temporal side of the right eye, temporal side of the left eye, nasal side of the right eye, nasal side of the left eye. Okay, so let's practice. We're talking about the field of vision. If I say the field of vision that I am concentrating on is the right side of the right eye, which one am I referring to? Good. What about the right side of the left eye? Perfect. What about the left side of the left eye? Awesome. the left side of the right eye. Splendid. What about the right side of the left eye and the right side of the right eye? Okay, so now I want your answers to be the right side of the right eye or the left side of the right eye. And on the left side, I also want you to use right or left. Okay? The temporal field of the left eye. Good. The temporal field of the right eye. Awesome. The nasal field of the left eye. Okay. The nasal field of the right eye. Okay. On which side are, oh, this one is a little bit more complex. Okay. I'm mixing two things. On which side are the right sides of the eyes? On which sides are the left sides of the eyes? All right. So that was basic. That was very basic. It's just about you knowing the temporal can also be known. The temporal of the left can also be known as the left side. The temporal of the right can also be known as the right side of the right eye. All right. Now let's now make it a little bit more complex. Okay. So one other thing is that this is the area of the external environment that can be seen by one eye, mono. All right. The area seen to the nasal side is called the nasal field, and the area seen to the lateral side is known as the temporal field. Uh, Now, the last two lines are the ones I want to dwell on. So, information from the right side of the visual fields have images falling on the left side of the visual cortex. Now, before we go to the visual cortex, let's just keep it at retina. And because we're talking about half of the retina, let me call it hemiretina. Okay, so information that is coming from the right side, let's look at the right eye. The right side of the visual cortex, okay, is going to fall on the left hemiretina. Okay, this is the retina, right? Right. Okay, so this is the left hemiretina and this is the right hemiretina. So again, information coming from the right side of the visual hemi of the visual right side of the visual field will fall on the left. They'll fall on the opposite side. Okay, so whether it's the right eye or the left eye, if it's coming from the right side, it's going to fall on the left. If it's coming from the left side, it's going to fall on the right. Okay. So go over this slide again. I suggest you go over it 3 times before moving on to the next slide. This slide is very wordy, but it's just there to summarize a few things. For instance, the visual nerve fibers leave the retinas as the optic nerve. Okay, this we have already learned. So they will pass caudally and they will meet at the optic chiasm. Okay, and once they're at the optic chiasm, or as they go through to the optic chiasm, they are now known as the optic tract because they're carrying everything. All right, and they are going to then synapse on the dorsolateral geniculate nucleus of the thalamus. We have already talked about this. They are then relayed to the calcrine fibers in an optic radiation, which we will talk about as well. All right. I think we will come back to this at another point. What I want to do is follow one eye and explain everything we're talking about. So let's start with the left eye. So if the light from the temporal field strikes the, okay, so light from the temporal field will strike the right hemiretiny. Okay, and then light from the nasal field will strike the left hemiretiny. Okay, let's see where these will go. So if we start from the temporal field will strike the right hemiretiny, and we'll find fibers from there going through the optic chiasm and crossing over to the right side and forming the optic tract, and then there will synapse. Okay, the first synapse is noted in the LGBs. From the LGBs, okay, they will go in more medially as the calcrine tract to the occipital lobe. So we just followed one. Okay, what about the one coming from the nasal? The one coming from nasal is going to hit this side, which is the left side. The left side of the left eye will maintain. It will go ipsilaterally. So ipsilaterally to move, go to the optic chiasm, ipsilaterally make the optic tract, and then it will have its synapse in the lateral geniculate body, but look, it is more lateral, and then it will move in the calcrine tract and go and synapse in the occipital uh, cortex. Okay, so that is the left eye. Let's see what the notes say. So the light from the temporal visual field strikes the right hemiretiny of the left eye. The ganglion axons from this part of the eye cross over to the right of the optic chiasm. Okay, the light from the nasal visual field strikes the left hemiretiny of the left eye, and uh, the ganglion axons from this part of the eye continue to the left. They go ipsilaterally. All right. What about, okay, the right eye? So the right eye, we can start with the temporal as well. So the temporal will go to the left hemiretiny, okay, and it will cross over, be more medially, and then form the calcrine to the occipital. The nasal will go to the right side and then keep ipsilaterally, and then synapse in the LGBs, keep more laterally, and then go to the. So the pattern is very, very simple to follow. You can always think of it as the temporals always cross and the nasals keep the same way. Okay, for me, that helps me remember. All right, then Another component that wanted to just make sure you know is that the retina also have ganglion cells that are known as large and small. So the large ones are the magno and the small ones are are known as the parvo. So the M cells respond to cones that are concerned with movement, um, and stereopsis, and these they project to a particular component of the lateral geniculate known as the magnocellular portion, whilst the P subtract input from one type of cone, and they are concerned with color, texture, and shape. So whilst the M ones are for movement, that one can, yeah, you sort of remember M for movement. The parvo are more for color, texture, and shape, and they project to the parvocellular portion of the LGB. So make sure that you remember that component. So if we look at it, if we look at the LGBs, where exactly are they synapsing on? We have very particular synapses. So you've seen on the right side that the parvos are the third, fourth, fifth, and sixth components, and whilst the more ventral components, one and two, are the magnocellular. So once you look at the magnocellular and parvocellular, please know that that's where they're coming from. So this also gives you where exactly our the ones that are coming ipsilaterally, where they synapse, and the ones that are coming contralateral, where do they synapse. You can start with the contralateral. So the contralateral, in this case, the ones coming from the left eye, you see that they're going to synapse in the sixth and the fourth, as well as the first. So we have magnocellular coming on to the first, and then their parvocellulars come to the fourth and the sixth. So that's 1, 4, 6. The ones that are coming ipsilaterally, they go for the magnocellular, okay, second. Okay, so you've seen they still maintain that lateral, okay, and then they also go on to innervate the third, okay, and the fifth. Okay, so you need to know the exact components where these sort of synapse on. So that's what this slide is saying, the exact components. What about uh, in the visual cortex? So the visual cortex is divided into the primary visual cortex and the secondary visual cortex. The primary visual cortex, V1, is looks at those that terminate direct visual signals. All right. So you have portions known as the macular areas of the retina near the occipital pore, and then we have the peripheral retinal terminating at or in the concentric half circles, and then you have the upper portions of the retina that are represented a little bit more superior, and then the lower portions inferiorly. I'll make a video on the visual cortex so that you understand it better. So at this point, I need you to download the second video, which is now talking about the visual cortex. All right.